Hope everybody's doing well on this Monday morning. Let's see, what I did last week was the roguelike stuff, and this week we switched back to crafting interpreters. Let me switch my screen over. There we go. Yeah, so last week we had played around with this. Oh, the roguelike's dead because I restarted my computer. But we're going to finish up One Night in the City last Friday, and I couldn't. But today we're going to be working on this bytecode virtual machine. We do have the, let's see, documents, dev, logs, ast. This is the Java virtual machine, the Java interpreter version of it, Jlocks ported to Rust. We finished all of that, and it's all up and on. Oops. No, that's RLTK. Here we go. Jlocks.ast. Here's the repo for it. So it's actually complete. It's probably not the best port. There's better ports, but it's my port, and so therefore I like it. So what we're going to need to do, obviously, is start off by creating a new repo for. Let's see, create repo. Oh, it's the plus sign, not the icon sign. Here we go. New repo, and we'll call this instead of Jlocks.ast, let's call it Jlocks bytecode. A bytecode interpreter, a bytecode virtual machine. There we go. Ported to Rust. We'll add a README. We got to git ignore for Rust, I guess. Why not? And we'll choose MIT license. There we go. Repo. Okay, so let's grab a clone of this guy and we can get started. Git clone. Except I do this, I think. Yeah, there we go. Okay, so right. So the first thing we need is a cargo.toml, and I think that's just the same one as I have for Jlocks.ast. I don't think I have anything special in here. Yeah, so this is just Jlocks bytecode. Yep, everything else looks good. And then we need to make dir source and vim source main. Normally Cargo does this for you. Oops, what was the error here? Oh yeah, I don't have a main yet. Okay, and that's going to complain at me. Fn main. Let's just put one in here really quickly. Cargo run. There we go. Now if I edit it, yeah, okay, so no errors this time. Okay, so I think we're up and running, ready to go. So this is the chapter right after the last one, right after the one about the byte. Oops, I don't know why I clicked on that. I didn't realize that went to the GitHub license. Neat. Okay, that's good to know. Yeah, if I go back one here, so we finished up inheritance, so got that working, and we're gonna have to do the same thing here, I guess, at some point. But let's kick things off. Our Java interpreter Jlocks taught us many of the fundamentals of programming languages, but we still have much to learn. First, if you run any interesting Jlocks programs in Jlocks, you'll discover it's achingly slow. The style of interpretation it uses, walking the AST directly, is good enough for some real-world uses, but leaves a lot to be desired for general-purpose scripting languages. We did have a few tests right in there, Jlocks.ast. There was that Fibonacci one. Yeah, Fib21, cargo run, Fib21. Oops. I forget how long that takes to run. Let's do it this way. Time, target. Oh, let's build release. Cargo, build release. So we can measure how long each fib number takes. Actually, I think there we go. Yeah, I have this break statement here. I want to get rid of the break statement and just go up to 10,000. Okay, so if I say time, target, release, oops, what's it doing? Target, release, there we go. Locks AST, fib21. All right, so it takes, less than 1/10 of a second of CPU time. That's not bad. But I'm sure if we went higher, it would take longer and longer. So we implicitly rely on runtime features of the JVM itself. We take for granted things like instance of in Java work somehow. Well, we had to destructure it ourselves in Rust, but that's okay. And we never for a second worry about memory management because JVM's garbage collector takes care of it for us. And in our case, since we used Rust, we relied on Rust's borrow checker and drop functionality to take care of the memory for us. Allocations and freeze. When we were focused on high-level concepts, it was fun to gloss over those, but now we know our way around an interpreter. It's time to dig down to those lower layers and build our own virtual machine from scratch using nothing more than the C standard library. All right, so how would we want to think about doing this in Rust, right? Because Rust, like I said, Rust handles a lot of the grunt work for us. In C you have to malloc, right? And use the malloc code function to allocate memory from the standard library, and then free. And so I imagine there's going to be a bunch of that in here. Whereas in Rust, we can get away with. Rust is kind of in that in-between state between Java and C, where it does a lot of stuff for you, but it doesn't do everything. All right, we already have ourselves a complete implementation of locks with Jlocks, so why isn't the book over yet? Part of this is because Jlocks relies on the JVM to do lots of things. If we want to understand how interpreter works all the way down to the metal, we need to build those bits and pieces ourselves. An even more fundamental reason is that Jlocks isn't sufficient is that it's too damn slow. A tree walk interpreter is fine for some kinds of high-level declarative languages, but for a general purpose imperative language, even a scripting language like Jlocks, it won't fly. Take this little script. On my laptop, it takes Jlocks about 72 seconds to execute. All right, well, let's try it out. Let's call it fib40. And I imagine my implementation of Jlocks is a lot slower than Java, so let's see what happens. There we go. All right, we'll see how long that takes. If it takes longer than 72 seconds, I'll kill it. An equivalent C program finishes in half a second. Our dynamically typed scripting language is never going to be fast as a statically typed language with manual memory management, but we don't need to settle for more than 2 orders of magnitude slower. We could take Jlocks and run it in a profiler and start tuning and tweaking hotspots, but that will only get us so far. The execution model, walking the AST, is fundamentally the wrong design. We can't micro-optimize that to the performance we want anymore. You can polish an AMC Gremlin into an SR71 Blackbird. We need to rethink the core model. This chapter introduces that model bytecode and begins our new interpreter Jlocks. I think this is taking longer than 72 seconds. Okay, let's kill it. And this went up to 21, so let's see if we can fiddle with this here. Let's try fib20 should go quickly, right? Yeah, 38 seconds. What are we printing first? Oh yeah, that's fib20. And it took 38 microseconds, I think, is the resolution on that. Or milliseconds, 38 milliseconds. So let's do fib30. Yeah, that's orders of magnitude slower. Okay, that took 3.8 seconds. And fib40 obviously was taking a lot longer than that. We can actually make this a little smarter, right? We can just say for I equals 0, I is less than 40, I plus plus. Actually, we can start at 1. right? And then have this. Instead of printing it, we'll say var result is this, that, and we can just say print fib of not 30, but I took plus this plus, I wonder if I have to group it like this. I don't know how picky the syntax is, even though I wrote this thing MS, right? Let's see if it compiles and runs. Yeah, expect expression. Okay, so we're going to have to be a little fancier here. Oh, did I not have the ability to add? How about this? Bar time after minus before. Maybe I can do it that way. Nope, still doesn't like it. I thought I could do this. Let me try running it this way. Bar a equals 1, print a plus foo. Yeah, that works. Print foo plus a plus bar. Alright, so what am I doing wrong? Line 6? Oh, line 6 expected expression. Do I have to say var? Actually, let's do this instead of saying time. It's going to be clock minus before. I've forgotten the syntax to, no. How do you do for loops? I thought it was like this. Oh, I++. There is no plus plus operator in Jlocks. There we go. So we can see how much longer it's taking each loop. 2.3 seconds, 3.8 seconds. So let's leave that running while we're reading. In engineering, few choices are without trade-offs. To best understand why we're going with bytecode, let's stack it up against a couple alternatives. Why not walk the AST? Our existing interpreter has a couple of things going for it. We already wrote it, so it's already done. That saves a lot of time, right? The runtime representation of the code directly maps to the syntax. It's virtually effortless to get from the parser to the data structures we need at runtime. And it's portable because it runs in any, because it's Java, right? But ours is Rust, so it's portable to any system that has a Rust compiler. Those are real advantages, but on the other hand, it's not memory efficient. Each piece of the syntax becomes an AST node. A tiny Jlocks expression like 1 plus 2 turns into a slew of objects with lots of pointers to them. References to them, right? The header parts of the bookkeeping syntax. Oh, this header business. Yeah. Each of these pointers add an extra 32 or 64 bits of overhead. We're sprinkling our data across the heap in a loosely connected web of objects does bad things for spatial locality. I wrote an entire chapter about this exact problem in my first book, Game Programming Patterns, if you really want to dig in. Yeah, that's where ECS designs came out of. Putting similar objects contiguous in memory speeds things up. All right, so we're already at 26 seconds at fib34. So this is pretty slow. This implementation is slower than the Java implementation on his laptop. So obviously we're doing something very inefficient in my port to Rust. Modern CPUs process data way faster than they can pull from RAM. To compensate for that, chips have multiple layers of caching, right? 100 times faster to get from the cache than to get it from main memory. So we're talking about reading memory from data from RAM into the cache. It doesn't just read one thing of data; it reads a whole bunch of data at once. And that way, if you need a bunch of sequential data, you get more cache hits, right? And so if you design your code to keep everything spatially located together, or similar things that you're going to need to parse together, then things go a lot faster. And so what they're saying is in the tree version of it, everything's everywhere, so it's very slow, or it's a lot slower than it could be. Even if objects happen to be allocated in sequential memory when the parser first produced them, after a couple of rounds of garbage collection, which may move objects around in memory, there's no telling where they'll be. All right, so this took 70 seconds at 36. It's going to go even longer for the rest of them. RST Walker has other overhead too around interface dispatch and the visitor pattern, but the locality issues alone are enough to justify better code representation. Alright, so why not compile to native code? If you want to go real fast, you want to get all of those layers of interaction out of the way, right down to the metal. Machine code, it even sounds fast. Compiling directly to native instruction set the chip supports is what the fastest languages do. Targeting native code has been the most efficient option since way back in the early days when engineers actually hand-wrote programs in machine code. Yes, they actually wrote machine code by hand on punch cards, which presumably they punched with their fists. You originally wrote it out on these big sheets of paper with ones and zeros, and then you went to the card punch with that. So almost. And then eventually the card punch became, well, there was also paper tape in there, and okay, getting distracted. If you've never written any machine code, or its slightly more human palatable cousin assembly code before, I'll give you the gentlest of introductions. Native code is a dense series of operations encoded directly in binary. Each instruction is between 1 and a few bytes long, and is almost mind-numbingly low level. Move a value from this address to this register. Add the integers in these two registers. Stuff like that. The CPU cranks through the instructions, decoding and executing each one in order. There's no tree structure like our AST, and control flow is handled by jumping from one point in the code directly to another. There's no indirection, there's no overhead, there's no unnecessary skipping around or chasing pointers. It's lightning fast, but that performance comes at a cost. First of all, compiling to native code ain't easy. Most chips in wide use today have sprawling Byzantine architectures with heaps of instructions that accreted over decades. They require sophisticated register allocation, pipelining, and instruction scheduling. And of course, you've thrown portability out. Spend a few years mastering some architecture, and that still only gets you onto one of the several popular instruction sets out there. To get your language on all of them, you need to learn all their instruction sets and write a separate backend for each one. The situation isn't entirely dire. A well-architected compiler lets you share the front end and most of the middle layer optimization passes across the different architectures you support. It's mainly the code generation and some of the details around instruction selection and register allocation, right, that you'll need to write afresh each time. The LLVM project gives you some of this out of the box. If your compiler outputs LLVM's special intermediate language, LLVM in turn compiles that into native code for a plethora of architectures. All right, so what is bytecode? On one end, a tree walk interpreter is a simple, portable, and slow. On the other end, native code is complex and platform-specific but fast, but bytecode sits in the middle. It retains the portability of a tree walker, which won't be getting our hands dirty with assembly code in this book. It sacrifices some simplicity to get performance boost in return, though not as fast as going fully native. Oh, hi, Epic. How are you? Epic says, I wish processor had a simple disable all fanciness and just one complete instruction after the other, so we could see how much all the magic gives us. I know Intel has switches to enable and disable various features of speed up, but not all of them. Epic says, I remember in 46 days some BIOSes allowed us to disable internal-external cache, which actually killed performance. Yeah. I think actually the 386 was the one that originally introduced burst mode for reading memory into cache. It goes pretty old, but yeah, I mean my first CPU that I played around with was the 6502, right? And that did exactly what you were saying. It fetches an instruction, executes it, and then fetches the next one. There's no extra black boxes of magic in between. So you knew exactly how long every instruction would take. You knew exactly how long every loop would take. Those are the olden days. All right, so structurally bytecode resembles machine code. It's a dense linear sequence of binary instructions that keeps overhead low and plays nice with the cache. However, it's a much simpler, higher level instruction set than any real chip out there. In many bytecode formats, each instruction is only a single byte long, hence bytecode. All right, imagine you're writing a native compiler from some source language, and you're given carte blanche to find the easiest possible architecture to target. So, you know, we play around with bytecode in advent of code, right? The int code machine, famously, was essentially a bytecode machine, and various other ones. Even the Cinecore challenge had a bytecode thing. So this is something we're pretty familiar with. So let me just see if we can skim to getting started here. What are we going to do here? We're going to have the problem with fantasy architecture is that it doesn't exist. You have to write an emulator, so that's what we're going to do. Emulation adds overhead, but in return it gives us portability. One of the first bytecode formats was P-code, developed by Nicholas Wirth's Pascal language. You might think a PDP-11 running at 15 megahertz couldn't afford the overhead of emulating a virtual machine, but back then computers were in their Cambrian explosion and new architectures appeared every day. Keeping up with the latest chips is worth more than squeezing the maximum performance from each one. That's why the P in P-code doesn't stand for Pascal, but portable. Oh, I didn't know that. Portable code. I do remember a long time ago playing around with, on an Apple II, a version of Pascal that did compile to P-code. So where do we begin? We begin with main. Shall I let this keep running? We're already at 3 minutes for each loop. And it's just going to get worse for 39 and 40. Oh, actually 39 is the last one. Okay, I'll let it finish out. All right, so what we need to do is, in order to port this to Rust, try to understand where he's going with the code, right? And we already have this done. I have a hello world written and running somewhere. Yeah, right here, hello world. So that part's done. So we're gonna have, this is common.h, obviously we don't need that in Rust. Pulling in a bunch of standard definitions, that's fine. Chunk, I guess, would be the first thing we would have to worry about, and we're going to start off with this enum. So enums in C are similar to enums in Rust, but not quite the same. They just define values, and I think they're limited to 32 bits for whatever historical reason. Or it might depend on the architecture. You might be able to give it flags to say make it 64 bits. So these aren't really byte codes, right? This is just a... I mean, we could just assign it values, right? Doesn't Rust allow you to assign values to enums? Rust enum assign value, yeah. Here's dog and cat. Yeah, so I don't know if we custom discriminant values, that's what they're called, for fieldless enumerations. If there's no data attached to any of the variants in enumeration, then discriminant can be directly chosen and accessed. You can't obviously have the same discriminant. And I guess this by default starts at 0 and works its way up. So maybe if I just assign the first one to 0, and then Rust will automatically assign the rest. But again, they're not going to be bytes. They're going to be of type opcode. So, whereas, you know, in C, you can kind of easily flop back and forth between, oh, I forgot to check here. Oh, this is still going. You can still flop back and forth between the enums and ints because they're, you know, they can cast to one another. So how would we do that in Rust? I guess would be a good question to ask. What would be the right approach here? And what I'm thinking is that maybe we could just write a from for it. We could do a opcode from a U8, and we can do a U8 from opcode and convert them back and forth that way. That'd be kind of on the annoying side only because every time we extend this chunk, obviously it's going to be more than just op return in here, right? There's going to be all the opcodes are going to go in here. So each time we add an opcode, we have to extend the from for both of them. But maybe that's the way to go. I should have started this in a different window, and fib39 is taking too long, so boom, I just killed it. All right, so locks bytecode. Let's go over there. We have our stuff. Git add dot git commit dash m set up rust executable. Or let's say binary. Okay. All right, so let's create a file called chunk. And we're going to say a pub enum op return and say opcode. Wait, no, I'm missing the syntax here. There we go. Pub enum opcode, and that just has op return, and then we can write a from, right? We can say impl from u8 for opcode. Oh, right, I was going to say equals 0, and that way each one of them will get their own value. Fn. Oh, I guess the easiest way to look up this would just say mod chunk and try to build it and see what fails. So I'm missing from. So it's going to be from the type. We don't need two windows there. So the type is a U8. Let's say call it code. And it's going to return stuff, which is opcode. So now we're just going to match code. 0 is going to be opcode op return, and everything else is going to result in a panic, or no, unimplemented. Will that check? Yes, so that checks. So we now have a from. So we can convert from U8 to opcode, and I guess we can do it the other way around. Impl from opcode for U8. Self. And is there a way to extract the value? Variant visibility. Is there a way to convert the number into an actual value? Huh. Let baz discriminant equal foo baz as, oh, just as use 32. So we can just say as use 32, right? We can just say code as U8. Yeah. So at least this one's easy, and maybe we don't even need to do this one. Maybe this one we get for free without having to do any extra work. Okay, so that's a chunk, right? And now we have this part done. For now, we'll start with a single instruction, op return. When we have a full-featured VM, this instruction will mean return from the current function. I admit this isn't exactly useful yet, but we have to start somewhere. These are particularly simple instructions for reasons we'll get to later, okay? Bytecode is a series of instructions. Eventually, we'll store some other data along with the instructions, so let's go ahead and create a struct to hold it all. Epic says, I believe unimplemented takes an argument. Oh, perfect, thank you. Invalid opcode. I wonder if can you do format in here? I'll let you do that, or do I have to ampersand it? Must be a string literal. Dang it. All right, that's fine. All right, yeah, that's better, because then we'll actually be able to see what the error is. Right, so now we're going to have an array of chunks, or a pointer to uint 8s. So what are we going to do there? I guess pub struct chunk is just going to be code vec of u8. And we kind of get all of the features of vec for free, right? At the moment, this is simply a wraparound array of bytes. Right. So this is what they were talking about before in the previous chapter, was we're going to have to do our own memory allocation and stuff like that. But, you know, Rust does that for us with vec. And I don't want to re-implement vec. There's no point in doing that when we can just have a regular old vec in here. So we can ignore this part of it, right? Dynamic arrays are one of my favorite data structures. That sounds like claiming vanilla is a favorite ice cream flavor, but hear me out. It's cache-friendly, dense storage, right? Because everything's contiguous. And I think vecs are stored contiguously, right? Constant time index element lookup, constant time appending to the end of the array. Those features is exactly why we use dynamic arrays all the time in Jlocks under the guise of Java's ArrayList class. Now that we're in C, we get to roll our own. If you're rusty, rusty on dynamic arrays, the idea is pretty simple. In addition to the array itself, we keep two numbers, number of elements, right? So, and vec has that already, right? Rusty vec. It has the capacity, the current capacity and the current size are known. Returns the number of elements the vector can hold without reallocating, versus the size, which is how many entries are, or len, it's len. How many elements are in the vector. So that's count and capacity here. So we don't need to worry about that in ours. And this is all talking about in C, how would you do it? Right, you've got a pointer to the code, you want to add one, you can just throw it at the end because our count is less than capacity. That's this example. But if we're already at the capacity, then we have to reallocate our array. And C actually has a function called reallocate, which allows you to do that. And if it can extend, it will extend. If it can't, then it will allocate a new region and then copy everything over. And then store the new value. Copying the existing elements when you grow the array makes it seems like appending an element is O of n, not O of 1. However, you need to do this copy step only on some of the appends. Most of the time there's already extra capacity, so you don't need to copy. Right. Alright, so init chunk is going to initialize all this stuff, but we already have it. I mean, we can create a new, right? We can impl a new. And so instead of init chunk, we're just going to say new, because that's the Rust style of doing it. All right, and it just sets the vector empty, essentially, right? There's no capacity. It would be nice, you know, if init chunk actually started with a capacity, right? Because then the first write to it wouldn't have to. I mean, you're going to do the work, but all right, we're not doing it in C, so we're not doing it this way. Dynamic array starts off completely empty. We don't even allocate a raw array yet. To append a byte to the end of the chunk, we use a new function, write chunk. This is where the interesting work happens, right? So this is where we do the work that we're describing above. If there's room, we stick it at the end of the current count. If there's no room, then we have to reallocate. Oh, he's got macros to do that work. Okay. I guess we're going to have more than one implementation of a dynamically arrayed or dynamically sized array. In Rust, we don't have to worry about it. So let's do a write chunk. Pub fun. We have a chunk, so we'll just call it write. And we're going to take a byte, which is U8. It doesn't return anything. Oh, we need a self. And then we're going to do self dot code dot push byte. So that all of that work is all done for us in Rust. So that's easy. The first thing we need to do is see if the current array already has capacity. If it doesn't, then we first need to grow the array. To grow the array, we first figure out the new capacity and grow the array into that size. So we have this memory.h. Right, here's grow capacity. capacity is less than 8, then make it 8, otherwise double the current capacity. Oh, I see. Yeah, it's passing in the old capacity here. Okay. I was saying, what should be the new size? And it looks like we start off with 8, and then if we go beyond 8, we double it each time. This macro calculates the new capacity based on the given current capacity. In order to get performance we want, the important part is that it scales based on the old size. We grow by a factor of 2, which is pretty typical. 1.5 times is another common choice. We also handle when the current capacity is 0. In that case, we jump straight to 8 elements and start it instead of starting at 1. That avoids a little extra memory churn when the array is very small, at the expense of wasting a few bytes on very small chunks. I picked the number 8 somewhat arbitrarily for the book. Most dynamic array implementations have a minimum threshold like this. The right way to pick a value for this is to profile against real-world usage and see which constant makes the best performance trade-off between extra grows versus wasted space. What does vec do? I'm curious now. Does it actually say in the docs how vec does it? Because it's going to do something very, very similar in that as it grows, I mean, I could do a vec with capacity here of 8 just to start it off at 8, but why? It doesn't say. I don't see anything here. I'm just trying to scan really quickly. Vec will never automatically shrink itself. That's fine. I guess we could take a look at the source, right? We can look at with capacity in here. Almost going to try to see if I could find fn push. If the length is equal to the capacity, then we reserve for push, and then we have some unsafe code. Wonderful. All right, and it just pointer writes. Okay, so I guess reserve for push. Let's take a look at how that grows. It's not here. Oh, it's in buff. And what is buff? What type is buff? Where's my scrolly bar? I don't see a scroll bar. Fn new. I guess we could say struct vec. So struct vec is a raw vec. Can we look at that code? Nope, apparently not. No. Why can't I look at raw vec? No, it doesn't have raw vec. Oh, it'd be nice to see that. Use crate raw vec. There is a crate for it. Rust crate raw vec. Here it is. Let's take a look at the repo. Source. Lib. So what does raw vec look like? Okay, and then the function we were looking was reserve for push. Oh, there's no push. Huh. Okay, I must be missing something because I saw a call to reserve for push, but I don't know where it points to. Right? Yeah, right here, reserve for push. All right. Well, I guess I'm lost. I'll have to look at that elsewhen. All right, and then we have a grow array, which does call the reallocate function. Oh no, there's a reallocate function. It's called realloc in C. So I guess he's writing his own reallocate. Once we know the desired capacity, we create or grow the size to that, grow the array to that size using grow array. Macro pretties up a function called a reallocate, where the real work happens. Macro itself takes care of getting the size of the array's element type and casting the result void star back to the pointer of the right type. Reallocate function is a single function we use for all dynamic memory management in Jlocks, allocating memory, freeing it, and changing the size of an existing allocation. Writing all of these operations through a single function will be important later when we add a garbage collector that needs to keep track of how much memory is in use. All right, so that's going to be interesting because we're not doing any of that, and I wonder if that's going to break everything we're going to do when we get to this garbage collector. Or maybe we can ignore the garbage collector completely because Rust is doing all the work for us. I don't want to rewrite raw vec or vec. So if new size is 0, then free the pointer, return null. It means we're clearing it. Otherwise, we're going to, we're calling C's realloc. So it's doing the work. It's kind of wrapping around the reallocate. When new size is 0, we handle the deallocation case ourselves. Otherwise, rely on the C standard library's realloc function. Interesting cases when both old size and new size are not 0. Please tell realloc to resize the previously allocated block. Right. That's the way realloc works. Allocation can fail if there's not enough memory, and realloc will return null. We got to handle that case. We will get that. Well, I guess we'll get a panic from Rust if we try to push and we run out of memory. Right, since all we passed in was a bare pointer to the first byte of memory, what does it mean to update the block's size? So under the hood, the memory allocator maintains additional bookkeeping information for each block of the heap allocated memory, including the size. So it already knows the size. Given a pointer some previously allocated memory, it can find this bookkeeping information, which is necessary to be able to cleanly free it. It's this size metadata that realloc updates. Many implementations of malloc store the allocated size of memory right before the returned address. Right. So, I mean, the way it typically works is you'll have, in malloc, you'll have like a chunk of header and a chunk of data. And then the data is what gets returned to the user. And then when we call realloc, it goes backwards in memory to find the header and then reads the header data that way. It's not really anything useful our VM can do if it can't get the memory it needs, but we can at least detect that and abort the process immediately instead of returning a null pointer and letting it go off the rails later. All right, that makes sense. Okay, we can create new chunks and write instructions to them. Are we done? Nope, we're in C now. Remember, we have to manage memory ourselves like in the olden times, and that means freeing it too. So we don't actually need to do that because in Rust, we'll just drop it when we need to drop it. All right. Oh, then they're reinitting it. Okay. Yeah, that makes sense because once you free it, freeing memory doesn't change the values, right, of code and capacity. We want to set those back to nulls. Okay. We deallocate all the memory and then call init chunk to zero out the fields, leaving the chunk in a well-defined empty state. To free the memory, we add one more macro. So we could say, oops, we could create a free if what we need is the same kind of semantics. We just say self code equals vec new. And that will free the memory that the old vec was pointing to, right? It drops all of those entries in that vec and then reinitializes code to an empty vector. So we can have that. That should work. We have 5 warnings because we're not using any of these things, right? That's okay. Like grow array, this is a wraparound call to reallocate. Oh, I see. We're just calling reallocate to free it out with the 0 size. Okay. And we have to pass in the type to free array. This is uint8 type. I imagine there'll be other types, right? Now that we have a little module for creating chunks of bytecode, let's try it out by hand building a sample chunk. All right, so in main, There we go. We can say use chunk star. And here in main, we can do is say let what chunk equals chunk new. That automatically does the init chunk. We can say chunk dot write opcode op return. Okay, that's going to be an issue because I think we're passing in a U8, and that might not automatically convert even with the from. And then chunk dot free. Right, we might have to say dot into. Yeah, expected U8 found enum chunk opcode, but I can say into. Yeah. I guess the other thing we could do is we could have a separate write opcode. And in chunk, we could say write opcode. Opcode. And just say into here. Right, yeah, that works. And then we could have a different write for each style of byte write that we're going to write the byte to. Don't forget the include. Okay, I didn't. Run that and give it a try. Did it work? Who knows? All we've done is push some bytes around in memory. Well, I mean, we can run it. Boom. Process exited 0, so we know it didn't panic or fail or anything. To fix this, we're going to create a disassembler. An assembler is an old-school program that takes a file containing human-readable mnemonic names for CPU instructions like add and mult and translates them to their binary machine code equivalent. A disassembler goes in the other direction. Given a blob of machine code, it spits out a textual listing of the instructions. We'll implement something similar. Given a chunk, it will print out all of the instructions in it. Jlocks user won't use this, but Jlocks maintainers will certainly benefit since it gives us a window into the interpreter's internal representation of code. And Jlocks are an analogous tool was the AST printer class, which we kind of ignored after a time, right? Commented it out and then sort of let it languish. I wonder if the disassembler is going to meet a similar fate. All right, so we're going to have a disassemble chunk. Okay, so maybe that goes in here. Pub fun, disassemble, self. And returns a void. Oh, and then we're going to have a separate disassemble instruction, which returns int. Okay. We don't know what this does yet. Oh, we need this text business in here. And what's it called? Just name, it says down here. I'm looking here. Let's type T. And then we're going to need a disassemble instruction. And it's going to be public. Does it need to be public? And it takes a chunk and an offset and returns. Now offset I'm going to use usize because I'm guessing that's an offset into the vector. We already have self, and then we're going to say offset usize. And then it returns an int, but I'm not sure what that's meant to be. Until we read the code, we're not going to see. So we'll get there. I'll just leave it no return code until we figure it out. So in main, we call disassemble chunk to disassemble all of the chunks we read. So chunk dot disassemble test chunk, right? And that's not going to compile because, well, it'll compile. It'll just give us warning that we're not using some of the. Yeah, we got foreign warnings on that. Okay. And here's the start of implementation file. So here's, oh, they're saying put this in debug.c. Except this is part of chunk, so I'm going to keep it here in chunk.rs instead of creating a separate. I don't know when I hiccup there, but debug.c has this disassemble stuff, but because it's part of the chunk, I'm going to just keep it as part of chunk and leave it there. So we're going to say print lin equals equals name equals equals, and then we're going to go through each. Oh, I see. It's returning an offset. Disassemble instruction takes an offset and returns an offset. So that means this needs to return a usize. And instead of doing this for business, because in C you can mess around with the loop index, I'm going to just say let mut offset equals 0, and then say while offset is less than self code len. We'll say offset is equal to self disassemble instruction offset. And there's no increment there, so we're just relying on disassemble instruction to return the correct value. To disassemble a chunk, we print a little header so we can tell which chunk we're looking at. Then we crank through the bytecode, disassembling each instruction. That way we iterate through the code. The way we iterate through the code is a little odd. Instead of incrementing offset in the loop, we let disassemble instruction do it for us. When we call that function, after disassembling the instruction at the given offset, it returns the offset of the next instruction. This is because, as we'll see later, instructions can have different sizes. Yeah, this makes sense. The core of the debug module is this function, disassemble instruction. All right, so we have the chunk and we have the offset. So we're going to print 4D, which is print bang, offset colon 04, I think, and then a space. I think that's the way it works. Let me put a 0 here and see. Oh, T cannot be used before. Oh, you can't. Name toString. Okay, so yeah, this offset colon 04 worked to get it leading zeros. Now we'll get the current instruction and then switch on the instruction. So we can just say match let instruction equals self code of offset match instruction op code op return. Oh, we have to say into and say opcode here. That way we can disassemble it directly into that, right? Opcode op return. We're going to return simple instruction op return offset. Self simple instruction op return offset. We don't increment the offset there. Okay, that's good to know. Everything else is going to be print lin unknown opcode. Oh, that could never happen because this into will fail. Right. This is just going to carry on. This is going to barrel on whether or not it works. But in ours, what we can just do is this will fail here, this into. Right, we're going to get a, where's my from? Here, and we'll get an invalid opcode here on that call to into. So we don't actually have to do anything else. We can just say match that. Boom. And then this just be offset plus 1. Although we should never get to that point. So we don't need that. And we haven't written simple instruction. Okay, so we're going to do that next. First, it prints a byte offset of the given instruction. This tells us where in the chunk this instruction is. This will be a helpful signpost when we start doing control flow and jumping around in the bytecode. Next, it reads a single byte from the bytecode at a given offset. That's our opcode. We'll switch on that. For each kind of instruction, we'll dispatch to a little utility function for displaying it. On the off chance that the given byte doesn't look like an instruction at all, a bug in our compiler, we print that too. Yeah, so this is where it'd be nice to have maybe I should panic here. Well, okay, I'll do this until we decide that we need to make this more complicated. For the one instruction we do have op return, the display function is this simple instruction. So we have now, I guess these don't need to be public, right? We're only going to call disassemble. So I'll make these private for now. Simple instruction. Self offset usize and return to usize, and we're going to just printf the name of the instruction. Oh right, I forgot the name. Let's do that. Println, just that. That's all we need to do, right? And then return offset +1. Yeah, okay. There isn't much to a return instruction, so all it does is print the name of the opcode and then return the next byte offset past this instruction. Other instructions will have more going on. If we run our nascent interpreter now, it actually prints something. All right, let's try it. Look at that, 000 op return, and there's test chunk right at the top. It worked. This is sort of the hello world of our code representation. We can create a chunk, write an instruction to it, and then extract that instruction back out. Our encoding and decoding of the binary is working. Of the bytecode, sorry, is working. So get add source, get commit -n section 14.4, I guess. Beginnings of the bytecode interpreter. I guess I should call it whatever it's called up here. Disassembling chunks. Okay. So 14.5, constants. Now that we have a rudimentary chunk structure working, let's start making it more useful. We can store code in chunks, but what about data? Many values the interpreter works with are created at runtime as the result of operations. 1 + 2. The value 3 appears nowhere in the code here, however the literals 1 and 2 do. To compile that statement to bytecode, we need some sort of instruction. That means to produce a constant, and those little values need to get stored in a chunk somewhere. In Jlocks, expr literal AST node held the value. We need a different solution now that we don't have a syntax tree. If we have bytecodes, how are we storing them? Okay, well, we won't be running any code in this chapter, but since constants have a foot in both static and dynamic worlds of our interpreter, they force us to start thinking at least a little bit how our VM should represent values. For now, we're going to start as simple as possible. We'll support only double precision floating point numbers. This will obviously expand over time, so we'll set up a new module to give ourselves room to grow. Typedef double value. So we're creating a value.h, which means we want a value.rs in Rust. And they're just saying typedef double, they're just redefining, I mean, Rust has that, right? We can say pub type value equals F64, right? Right? And now we have an F64. But I don't know if this is actually the way we want to do it. Let's keep reading. This typedef abstracts how Locks values are concretely represented in C. That way we can change the representation without needing to go back and fix existing code that passes around values. Alright, back to the question of where to store constants in a chunk. For small, fixed size values like integers, many instruction sets store the value directly in the code stream right after the opcode. These are called immediate instructions because the bits for the value are immediately after the opcode. That doesn't work well for larger variable size constants like strings. In a native compiler to machine code, those bigger constants get stored in a separate constant data region in the binary executable. Then the instruction to load a constant has an address or offset pointing to where the value is stored in that section. Most virtual machines do something similar. For example, the JVM associates a constant pool with each compiled class. That sounds good enough for Jlocks to me. Each chunk will carry with it a list of the values that appear as literals in the program. To keep things simpler, we'll put all constants in there, even simple integers. In addition to needing two kinds of constant instructions, one for immediate values and one for constants, in the constant table, immediates also force us to worry about alignment, padding, and endianness. Some architectures aren't happy if you try to, say, stuff a 4-byte integer at an odd address. That's true. All right, defining a new struct and manipulation functions each time we need a dynamic array of different type is a chore. We could cobble together some preprocessor macros to fake generics, but that's overkill for Jlocks. We won't need many more of these. All right, so it looks like we're going to have another vec of values this time. The constant pool is an array of values. The instruction to load a constant looks up the value by index in that array. As with our bytecode array, the compiler doesn't know how big the array needs to be ahead of time, so again we need a dynamic one. Since C doesn't have generic data structures, we'll write another dynamic array structure, this time for value. So I think what this translates into pub struct value array, which is going to just be values, vec of value. And I can already see that we might have some issues around this, especially if we're going to hang things off of value. We have init, write, and free, just like before. So impl value array, pub new, self values, vec new, and we also need write, write, self, v, I guess value. Let's keep their naming. And that works. It's copy, right? You can just do it as a copy and it doesn't return anything. It's a void. Self values push value. And then free is pub fun free, not self. Self values is vec new. All right, and that all checks. So that's essentially all of this. Fortunately, we don't need other operations like insert and removal. Memory management macros we wrote earlier do let us reuse some of the logic. Okay. C and Stone Age modularity story. Where were we? Right. So when we initialize a new chunk, we initialize its constant list too. Oh, okay. I missed this. Right. So in chunk, we're going to have a value array of constants. Okay. So let's pull that up. So it's not going to just be this. It's also going to be constants, which is a value array. Interesting. Yeah. Use values. Oh, value, colon, star. Create value. Thank you. And then we have to initialize it. Constants. Value array new. All right. This feels a little awkward to me, but let's keep going. Why wouldn't we just say vec right in here? Maybe that would be the simpler way to do it, a vec of value in here, rather than having this separate interface. But let's keep going. There's free. So when we free this, we're going to have to, oops. I meant to go down here, then say self constants is vec new. Oh no, value array new. Here we go. And then we're going to have add constant. So we have this add constant here. Next, we define a convenience method to add a new constant to the chunk. Our yet to be written compiler could write to the constant array inside chunk directly. It's not like C has private fields or anything, but it's a little nicer to add an explicit function. So let's say pub fun add constant mut self value. And it's just going to call right value array, which we already have right for, self constants right value. So now we have this extra layer of indirection. All right. And I understand why. Oh, and it returns an index. Okay, which has to be a usize, right? Maybe this returns it. Let count is equal to self values len. We'll push it and return count. Right? Because we're returning count -1. We're returning how many there were. Well, basically the index. So once we write to it, the index goes from 0 to 1, then we want to return 0. So that's all I'm doing here. I just did it without the subtraction. After we add the constant, we return the index where the constant was appended so we can locate the same constant later. All right. So we can store constants in chunks, but we also need to execute them. How do you execute a constant? In a piece of code like print1, print2, the compiled chunk needs not only to contain the values 1 and 2, but know when to produce them so they are printed in the right order. Thus, we need an instruction that produces a particular constant. Okay, trying to understand that. When the VM executes a constant instruction, it loads the constant for use. This new instruction is a little more complex than op return. In the above example, we load two different constants. A single bare opcode isn't enough to know which constant to load. I'm being vague about what it means to load or produce a constant because we haven't learned how the virtual machine actually executes code at runtime yet. For that, you'll have to wait till you get to, or skip ahead to, the next chapter. Bytecode instruction operands are not the same as the operands passed to an arithmetic operator. You'll see when we get to expressions that arithmetic operand values are tracked separately. Instruction operands are lower-level notation that modify how the bytecode instruction itself behaves. Right, okay. That I get. To handle cases like this, our bytecode, like most others, allows instructions to have operands. These are stored as binary data immediately after the opcode of the instruction stream, and lets us parameterize what the instruction does. So op return, oh, they're using 1 as op return and 0 for op constant. Okay, we can do that too. Each opcode determines how many operand bytes it has and what they means. For example, a simple operation like return may have no operands, whereas an instruction for load local variable needs an operand to identify which variable to load. Each time we add a new opcode to Jlocks, we specify what its operands look like, its instruction format. In this case, op constant takes a single byte operand that specifies which constant to load from the chunk's constant array. Since we don't have a compiler yet, we hand compile an instruction to our test chunk. All right, so I see this, we added op constant to the chunk. So let's go to chunk here and add op constant. And for some reason, we've decided that's going to be 0 and op return will be 1, which means we need to change this to op constant and this to opcode op return. Hopefully that's not going to be a pattern throughout this. Hopefully we just append, or he might be doing alphabetical, which would be kind of annoying. So if that's true, then we're gonna ignore the order and just do it this way. All right, so we have a right chunk op constant and a right chunk constant, and we have this add constant, which gets, oh, right. Add constant right now returns a usize, which is no good. It needs to return a U8 because we're writing it into our chunk, and our chunks are just U8s, which means we can only have 255 constants, I guess. All right, so add constant returns the index. Then we're going to write chunk op constant and the right chunk constant. So which means we need a write, just general write, pub fun write, which we had before. I guess this should be called opcode. doesn't like that because I left out. Ooh, I left this out. If we try to run now, the disassembler is going to yell at us because it doesn't know how to decode. Okay, so before we do that, let's fix that. Let's do it in the same order. Constant. Self. Oh, this is a constant instruction now. Op constant with offset. Okay. And then that looks like this. So let's write this. I know I still have to go back up and do this. I haven't forgotten. Constant instruction. Self. Name stir. Offset usize. And returns a usize. And what we're going to do now is we're going to look up the constant. And we're going to call print value on the constant. All right, so we can just say let constant equal self chunk of offset plus 1, and that's a U8. Okay, and then we say print F, so this is print bang, name colon 16. I don't know if I can do a minus in there. I can try it. And then constant 4 space single quote. Then print value of the constant's values. So we're going to have to maybe have a print value on here on the value array. But we're passing in a value to print. I mean, so like what I'm thinking is what we want to do is say self dot constants dot print value of constant, or we want to say self value of get a constant dot print value, or maybe look up something like that. What would be the right way to do this? And then print ln single quote there. What would be the better way to do this? So we have two options here, right? We can say this, or we can say self constants print value constant. Right, and doing it the second way just means we say pub fun print value self which usize print ln, no, just print bang, and then it's just self values of which. I think that maybe that's the right way to do it. Let's find out if that ruins us, or if this will. Oh, it's not self chunk, self code. Yep. And it's returning usize. Oh, we have to return something. They left that part out of the code. This is just the print stuff. Return offset plus 2. Okay. Offset plus 2. As usize. Okay. All right. Now I have to go back all the way back and take a look at this. We want to write this in main. So in main, we did the init chunk. That's this thing here. Then we'll say let constant equals chunk add constant of 1.2. Oh. I have it passing in as value. Is that going to work? Let's see what Rust does with that. And then we say chunk.write opcode opcode op constant and chunk dot write constant. Let's see what Rust does with this. It didn't complain, but we do have 2 warnings. What are the warnings? We're not using free on value. Oh. Yeah, we can do that. Let's do that here. So, constants free? I guess we don't need to do that, right? Sure. All right. This feels really awkward, but okay. I mean, it doesn't feel very rusty. Maybe, yeah. So let's keep going. If we run this now, is this going to work? We don't have any errors or warnings. All right. I mean, it worked. We have op constant 0. What's the 0? Oh, that's the index into the constant array, right there. And the minus worked. It's all the way on the left, so that's good. And then we have 1.2 as our constant. The print value worked. Okay, so maybe this is the right approach. Self constants print value, and then constants as usize. I mean, this would be the other way of approaching it, but let's do it this way for now. So I think we've got this done. Right. This instruction has different instruction formats, so we write a new helper function for it. There's more going on here. As with op return, we print out the name of the opcode, then we pull the constant index. Right, that's what we're doing here. We print that index, but that isn't super useful to us human readers, so we also look up the actual constant value and display that value itself. So this requires some way to print a Jlocks value. So that's what we did here with the print value. Limitation is just %G. We're just printing it out however Rust wants to print it. Does Rust have a G formatter? It does not. And it's E. What did I do? It just says EOPBX. That's it. Yeah, lower X spin upper X, but there's no F versus G, floating point versus double. Okay. Remember that disassemble instruction also returns a number to tell the caller the offset at the beginning of the next instruction. Where op return was only a single byte, op constant is 2, one for the opcode and one for the operand. Okay. So that's all good. Let's check this in. Actually, you know what we can do is Clippy, right? I haven't done that yet. Oh, right. I forgot to undo that change. Okay. Now we should be good. All right. So git add source, git commit, section 14.5, and it was called constants. Where is it? Constants. All right, 14.6, line information. Chunks contain almost all the information that the runtime needs from the user's source code. It's kind of crazy to think that we can reduce all of the different ASD classes that we created in Jlocks library down to an array of bytes, an array of constants. There's only one piece of data we're missing. We need it even though the user hopes to never see it. When a runtime error occurs, we show the user a line number of the offending source code. In Jlocks, those numbers live in tokens, which we in turn store in the AST nodes. We need a different solution for Jlocks now that we've ditched syntax tree in favor of bytecode. Given any bytecode instruction, we need to be able to determine the line of the user's source program that it was compiled from. There are a lot of clever ways we could encode this. I took the absolute simplest approach I could come up with, even though it's embarrassingly inefficient with memory. In the chunk, we store a separate array of integers that parallels the bytecode. Each number in the array is a line number for the corresponding byte in the bytecode. When a runtime error occurs, we look up the line number at the same index in the current instructions offset in the code array. All right, so this is really what I'm looking at here is we're really trying hard to have a bytecode thing, which is an array of bytes that we execute. We could, theoretically, instead of doing this with the op constant, having a constant array with Rust, we can say probably enum opcode and store the thing right here, op constant value, right, and op return. This would mean that we can't store these as U8s, but as opcodes, and each opcode would have the whole thing in there, right? I don't know if that would be, for Rust's point of view, more efficient. And then the line numbers, how would the line, so instead of doing it this way, we could say, you know, struct op struct, we could say like a chunk pub struct chunk entry, which contains code opcode. Okay, I don't care about typos, and then usize line number, or line usize, and then oops, this would then be a vec of chunk entries. So each one would have the line number, it would have the opcode, and the opcode itself would have the value, and all that kind of stuff. And any, you know, whatever other opcodes we have, all the information could be stored here as like a tuple, or even as a struct, right? That might be a more rusty approach, and maybe that would be a thing to do after we've gone through this whole book, is to make it rusty. But meanwhile, we're going to have lines here, right? We have code, we have lines, we have constants. So lines it is, and lines is just an array of offsets. So we get this for free, we get this for free, we get the, oh, now right chunk needs a line number. Okay. And because we have two different ones, we're going to have to do two different things. Line usize, self lines, push line, and then the same thing here. All right, so that's what right chunk changes into, right? So we're going to have to add the line for that. And then this also has to grow and shrink, but we get that for free from Rust. And then we're going to go to disassembling line information. I think this is all we need to do to push the lines. We do have to change main, right? Let's flip over to main. Oh, we need lines. And I'm surprised Clippy didn't complain about a lack of default, but okay. Yeah, so now we need line numbers here, and it looks like we're just using 1, 2, 3 as our test line number. Okay. Let's try this out with our little artisanal chunk. First, since we added a new parameter right chunk, we'll need to fix those calls to pass it in. So there is 1, 2, 3, 1, 2, 3, 1, 2, 3. Once we have a real front end, of course, so while it will track the current line as it parses and passes it in. Okay. We don't have a real front end yet. Now that we have line information for every instruction, let's put it to good use. And our disassembler is helpful to show which source line each instruction was compiled from. That gives us a way to map back to the original code when we're trying to figure out what some blob of bytecode is supposed to do. After printing the offset of the instruction, the number of bytes from the beginning of the chunk, we'll show its source line. So we have to go back to chunk here and look at disassemble instruction. We still print out the offset here, but now before we do anything else, if offset is greater than 0 and chunk lines of offset is equal to chunk lines of offset minus 1, we print a vertical bar. Otherwise, we print the line number. Okay, I think that translates almost exactly into Rust. Offset is greater than 0 and chunk self lines of offset is equal to self lines of offset minus 1. Then print bang. This looks like we're going to do 1, 2, 3 spaces, a vertical bar, and a space. Like that. Else, print bang. 4. Right? Self, lines, offset. Bytecode instructions tend to be pretty fine-grained. A single line of source code often compiles to a whole sequence of instructions. To make that more visually clear, we'll show a vertical bar for any instruction that comes from the same source line as the preceding one. The resulting output for our handwritten chunk looks like this. Right, so let's try this out. Come on. Oh, I missed a space. There we go. Yep, that looks good. I guess we're assuming there's only going to be up to 4 or up to 10,000 lines. We have a 3-byte chunk. The first 2 bytes are a constant instruction that loads 1.2 from the chunk's constant pool. The first byte is the constant opcode, and the second is the index into the constant pool. The third byte at offset 2 is a single byte return instruction. In the remaining chapters, we'll flesh this out with lots more kinds of instructions, but the basic structure is here, and we have everything we need now to completely represent an executable piece of code at runtime in our virtual machine. Remember that whole family of AST classes we defined in Jlocks? In Clocks, we've reduced that down to 3 arrays: bytes of code, constant values, and line information for debugging. This reduction is a key reason why our new interpreter will be faster than Jlocks. You can think of bytecode as a sort of compact serialization of the AST, highly optimized for how the interpreter will deserialize it in the order it needs as it executes. In the next chapter, we will see how the virtual machine does exactly that. All right, so let's commit these changes. So git add source, git commit -m, section 14.6. Oops. Section. Oh, there we go. And I think it's just called, I forget what it's called. Line information. All right, what are the challenges here? Our encoding of line information is hilariously wasteful of memory. Given that a series of instructions often correspond to the same source line, a natural solution is something akin to run-length encoding of the line numbers. Devise an encoding that compresses the line information for a series of instructions on the same line. Change write chunk to write this compressed form and implement the getLine function that, given an index of an instruction, determines the line where the instruction occurs. Hint, it's not necessary for getLine to be particularly efficient, since it's called only when a runtime error occurs. It's well off the critical path where performance matters. Yeah, okay. That's an interesting challenge that I will pass on. Because op constant uses only a single byte for its operand, a chunk may only contain up to 256 different constants. That's small enough that people writing real-world code will hit that limit. We could use 2 or more bytes to store the operand, but that makes every constant instruction take up more space. Most chunks won't need that many unique constants, so that wastes space and sacrifices some locality in the common case to support the rare case. Epic says, "Will this be a register or stack-based VM?" I don't know. I haven't read far enough in advance yet. I think a stack-based is the simpler thing to implement, right? But we'll see. To balance these two competing aims, many instruction sets feature multiple instructions that perform the same operation, but with operands of different sizes. I'll leave our existing 1-byte op constant instruction alone to define an op constant long instruction and stores the operand as a 24-bit number, which should be plenty. Implement this function. It adds values to chunk's constant array and then writes an appropriate instruction to load the constant. Also add support to disassembled op constant long. So we could do that, right? Defining 2 instructions seems to be the best of both worlds. What sacrifices, if any, does that force on us? Yeah, I mean this would be fairly straightforward to implement. I'm not going to do it right now, but it seems straightforward, right? Our reallocate function relies on C's standard library for dynamic memory allocation and freeing. Malloc and free aren't magic. Find a couple of open source implementations of them and explain how they work. All right, I don't need to do that. Implement reallocate without calling realloc, malloc, or free. You're allowed to use malloc once at the beginning of the interpreter's execution to allocate a single big block of memory. which your reallocate function has access to. It parcels out blobs of memory from that single region, your own personal heap. It's your job to define how it does that. Yeah. I mean, that's... Yeah, so basically just write your own. Roll your own allocator. The only issue with that, of course, is that if you malloc once at the beginning of interpreter and never use it again, what if you run out of space? Whereas using the C library stuff, you won't run out of space until you run out of memory. Design note, test your language. We're almost halfway through the book, and one thing we haven't talked about is testing your language implementation. That's not because testing isn't important. I can't possibly stress enough how vital it is to have good comprehensive test suite for your language. I wrote a test suite for Jlocks. Before I wrote a single word of this book. Those tests found countless bugs in my implementations. Oh, okay. I wonder if we should try that against our Jlocks thing and see how many things are broken. How does this work? I don't see how do you run the tests, or do you just run them and let's take a look at a test here. Empty file. Oh well, empty file. Duh. Precedence. Okay. I mean, I can see where it's saying okay, it's got a comment and expecting a true. But how do you run this? Is there some way to run it from up here? Hacking on the book. Where's tests? Building the interpreters. Testing. Here we go. I have a full Jlocks test suite that I use to ensure the interpreters in the book do what they're supposed to do. The test cases live in test. The Dart program. Oh, I might have Dart installed. Dart not found. Okay. I guess I don't have Dart installed. Dart, Mac OS, install Dart. I think it's just brew, right? Brew install Dart. Get Dart. Oh, you need tab. Okay. Let me do that while I'm looking at the test suite. Oh, dang it. Okay. I'll do that offline. My admin, the admin user I have on this machine has the lock, so I don't want to log in as my admin right now. All right, so make test Clocks, make test Jlocks. Okay, so testing your implementation. You are welcome to use the test suite as the test runner to test your own Jlocks implementation. The test runner is tool bin test Dart and can be given custom interpreter. Okay, so I could just run using Dart directly. Let me see if I can just do it quickly over here in a separate window. Oh wait, I do have Dart installed. I just don't have user local bin on my path here. Oh yes, I do. Hang on. Oh, I see what's going on. Okay, I got to fix that. Emil says, not sure if you're aware, but you wrote commit incorrectly and did not commit your last change. Oh, thank you. Thank you. I was not aware. Thank you for pointing that out. All right, so yeah, okay, I see what the issue is. I do have Dart installed, but I screwed up the permissions on it, so I don't have that there. I will fix that offline and then get that working. And then tomorrow maybe we'll take a look at running our Jlocks AST against Dart. You still need to tell it which suite of tests to run because it determines the test expectations. If your interpreter should behave like Jlocks, use Jlocks. If it should behave like Clocks, use Clocks. Okay, yeah. Let me get that set up offline, and I will run that tomorrow and see how it looks. Yeah, I have a permissions issue here. Let me just. Yes. Okay. Yeah, I will fix that. I'll fix that offline. All right. But that's good. That's good to know. Test the report. And yes. Actually, one of the things I wanted to do here was just write some internal tests, right? We should be able to write tests to test all this stuff. And if I were to like write this from scratch without using this design, I'd probably start with TDD, write a test, write the code, make sure it works. All right. So tomorrow, I'm gonna wrap up here, and then tomorrow we will do a virtual machines. We're going to start with chapter 15. Let's push this up to my repo, which is this one. Yes. Jlocks bytecode. So here we go. We got 5 commits. Right. So that's what I've done so far. That's good news. And then tomorrow we're going to look at this virtual machine thing. It looks like a VM is going to contain chunks, multiple chunks. Uh-oh, are we going to rewrite a chunk expander? I'm just scanning forward to see if... No? Okay, I was looking forward to see... scanning forward in this to see if we're going to have chunks with capacities and sizes and stuff like that, but it looks like not. All right, so we will look at that tomorrow. Meanwhile, thanks everyone for hanging out with me. I don't see anybody currently doing Rust streaming. Let me do a refresh here and see if somebody gaming out there. I don't see anybody. Okay. So tomorrow we're going to look at a virtual machine, and I wish you all a great day, and thank you for hanging out with me, and take care.